On December 5th, 2022, researchers at the Livermore National Laboratory achieved fusion ignition, a milestone that has been decades in the making. This breakthrough in nuclear fusion research could pave the way for sustainable, carbon-free energy that could help address the climate crisis. To help us understand this breakthrough and its potential, I've invited a colleague of mine who is a clean energy researcher to join us today. Let's be honest, nuclear fusion could be a tricky topic to wrap your head around. So we're going to break it down in plain English and explore the ins and outs of this technology. We'll discuss the science behind it, its potential as a sustainable and abundant energy source, and the safety concerns that come with such a powerful technology. So, if you're looking to get up to speed on the latest breakthrough in clean energy and what they mean for the future, you're in the right place. Sit tight and enjoy this episode of the Sustainability Nuggets podcast. Welcome to the Sustainability Nuggets podcast. I am Lawrence Livermore.
And I'm testing for Lawrence.
On this podcast, we'll learn about sustainability by discussing various related topics while focusing on three pillars: the economy, the society, and the environment. Hello, Shola.
Hi, Ramsey.
I'm happy that you're on here today. So can we just start by you introducing yourself to the audience?
Oh, yeah. I'm Alicia Johnson. I'm currently a PhD student at the University of South Florida. I mainly work in catalysis and clean energy research. And our aim, which is usually to convert biogas to diesel and other renewable energy source, like jet fuel and all of that stuff like that. And for that, we need to develop catalysts. Design and development of catalysts is usually a very rigorous process. Experiments at national labs using neutrons, which are generated used from nuclear, and also like X-ray sources. They control big X-ray sources like Brookhaven National Lab, Stanford Research Facility, and also Oak Ridge National Lab. That is where we do most of our neutron experiments.
Okay, I know you're in catalysis, but like, what's your passion as a whole? Is it just catalysis, or do you have extra passion for like certain areas of research?
I got into catalysis because I love energy. My undergraduate was in petroleum engineering, so you could tell like I've always been in the energy space. Maybe fossil, started from fossil, then transition into renewable because that is the future. So my passion has always been renewable energy. Catalysis, I see it as a tool that we use to arrive at our final destination. Like just we'll be talking about nuclear as well.
So let's get into this nuclear fusion. Can you explain the process of nuclear fusion and how it differs from nuclear fission? Because these are two things, and I'm sure people do not know the difference.
So that is what some people refer as confusion, because to a general, to a layman, people on the street, people who are actually going to benefit from the technology, it's really difficult to differentiate between what fusion or what fission is. Fission is generally what we're used to. That is a well-developed technology. So fission is when you split a large atoms into two or smaller ones. So this is usually we use uranium or plutonium. Those are the two common elements that we use in this process. So a neutron strikes this and it splits them. They are radioactive material. They produce radioactive material. So this is where the problem is. When you split two atoms, you generate energy, right? So energy can then be converted into electricity as we have in nuclear power plant. On the other hand, nuclear fusion is when you merge two atoms together. So you take two smaller atoms, you merge them into a bigger. What is not so clear to most people, or the question most people ask is that, how does merging two atoms? I can understand when you split two atoms, you can generate energy. But how do you merge two atoms and generate energy? So in most cases, we use helium hydrogen isotopes, deuterium, tritium. So that is 2 and 3 hydrogen isotopes. When you match them together, you produce the largest atom like helium. In this case, 1 plus 1, which is hydrogen and hydrogen, does not necessarily equal 2. It equals to less than 2 because the final nucleus, you imagine 2 nucleus, the final nucleus is slightly less than 2. You remember that energy cannot just be created or destroyed, right? So the mass that is remaining, that small amount of mass that is not accounted for, is converted into energy through Einstein's E equals to mc squared. So that is how you could generate infinite amount of energy based on the conversion of mass through the equation.
So you said infinite amount of energy. So that's another question. In our normal power plants, so let's even go to fossil like natural gas plants or even coal plants, you have inputs, right? You're inputting the gas is being combusted or the coal is being burnt. And so like there's constant input of a feedstock. So is this how nuclear fusion work? Because you talked about isotopes of hydrogen. I'm going to call it D and T because I don't know how to pronounce it. So D and T. So do we need to constantly, like when we think of the plant, is there a constant flow rate of D and T into the nuclear fusion plant to keep up the energy being produced?
Okay, so anything we're talking about now, it's possible design for a power plant, right? On December 5th was the first time in Lawrence Livermore National Lab at the National Ignition Facility that we achieved net gain in a nuclear fusion experiment. So that is more like when the Wright brothers, when they built the first plane that only flew over 120 feet, right? They immediately develop an hypersonic, supersonic flight immediately, right? It took years. So, but we already know in the future we can do this, right? So any power plant, we can only discuss hypothetically how it will work. The final design will obviously be different from it. So back to your question, before nuclear fusion reaction, in this case, if you're going to combust coal, you need carbon, you need coal and oxygen, right? Then you need to start a fire. Then the fire becomes self-sustained. When you run out of coal or you run out of oxygen, the reaction, which is the burning reaction, stops at that moment, right? So it's the same thing. Is that when you run out of deuterium or titanium, the reaction has to stop, right? But you need to be able to start it first. So that is the major achievement that was done on December 5th, is that they achieved a process called ignition, where the nuclear fusion was able to self-sustain enough to produce more energy that was put in it to achieve a net gain energy.
So now we're talking about D and T as the fuel that was used. Where is this gotten from?
So for deuterium, both deuterium and titanium are actually rare on Earth, but compared to titanium, deuterium is more abundant. In 1 out of 5,000 hydrogen atoms on planet Earth, you will get deuterium.
Okay.
And if we then have to look, where do we have the most abundant hydrogen atom? The sea, right? The seawater is the H2O, that is the gray of hydrogen. So we've perfected to some extent the technology for separating heavier water, which is D2O from ordinary water, that we can obtain deuterium atoms. The titanium, on the other hand, is extremely rare. Currently, in the entire world, we have about 20 kilograms of titanium. In fact, you would have seen a lot of science magazine articles flying around it, but maybe we would not have enough deuterium to even start the first experiment. Titanium, to start the first experiment because of the rarity. And of course, there is a lot in this nuclear fission. There's a lot of facilities that is involved, and we need a lot of titanium. Titanium is gotten from lithium. It needs to undergo a nuclear fission where you just you add a neutron, you can split lithium into titanium.
Okay.
What we use in battery technology. But also remember that we do not have that in extreme abundance, right? That is also why people are moving away from lithium-ion battery, because we don't have enough lithium. But hypothetically, we also believe that the moon has a lot of lithium. So,
the moon?
Yeah. So what if we can build a nuclear reactor on the moon? So we extract lithium on the moon, convert it to titanium on the moon, then we can transport it back to it. So that is also some possibility that people have been considering.
So apart from D and T, are there other like fuels that can be used in this nuclear fusion?
Technically, yes. You can use other elements for nuclear fusion. The way nuclear fusion works is this is the same principle that the sun uses, for example. The sun produces all the energy we receive through nuclear fusion. The surface of the sun, for example, is about 5,500 degrees Celsius degree, while the core is about 15 million degrees Celsius. Because it's super dense and the core is very hot, it could combine atoms, even larger atoms. We need to be able to match these two atoms together. So the larger the atoms, the more difficult it is to match together. So that is why we go for one of the most simplest atoms, that is hydrogen isotopes. So if you're going to go to 2 or 3 atomic mass, then you need more dense, you need the core to be denser, you need higher temperature. The condition just does not it's not as favorable as when you use the hydrogen isotopes. So that is the technical challenge, but theoretically you could make any atoms together.
So let's talk about how power is actually really, I know like it's still in research, we're talking hypothetically, but like how can large scale power generation be achieved from this technology, like when comparing it to other renewable energy sources?
Okay, so that's a good question. And before we can talk about the large power plant, we have to talk about what this process is right now in the lab, then how they can scale it up. For example, let's just describe the National Ignition Facility at Lawrence Livermore that produced the first net gain. So in this facility they started building this in the 1990s, and the aim was to achieve the first ignition, nuclear fusion ignition. And obviously the challenge has been very, very, very difficult. Some people call them never ignition facility, and I have at some point become nearly ignition facility, but now it's ignition. The way the process works is that they produce a major laser from the oscillator, and this is divided into 92 different lasers. So it goes to 92 beam lines, and in that beam line, it rocks back and forth to increase the energy of the laser. They are small pulses. Let me keep that. This is pulses. It's a single pulse, and this pulse lasts about 1 billionth of a second. So it's extremely so ultra fast. It goes through the beam line, it goes for a while to increase to the energy, then it goes through some filtering, it goes through some processing, and also the aim is there is a target that the laser has to hit. And the aim is that all these lasers from 192 different beam lines come at the source at exactly the same time. So the target is a hollow. Inside that hollow jacket, there is a small capsule of deuterium and titanium, which is loaded at cryogenic temperature because it has to be solid. So think of solid hydrogen isotopes, right? In a small capsule, so we're talking of on a millimeter or micron scale. And need to compress the capsule uniformly, because if you don't, then if there is a space for any of the deuterium, then it could easily just squeeze out. So it needs to be uniform in all directions. So the aim is that when you compress the deuterium and the titanium together, so you squeezing, let's think of it like you squeezing from a basketball now to a very tiny small pieces in a billionth of a second.
Mm.
So what happens is that the center, the core, becomes too hot immediately. So what the laser is transferring is the UV energy that just compresses, right? But you do not directly transfer it. But the core becomes hot immediately, because that is physics, right? When you compress something, it's like when you expand
increase
something
in pressure.
Yeah, it's compressed. The core is about 100 million degrees Celsius. It's one of the extreme conditions you can get in the universe. If the reaction then ignites or starts, it propagates out. So the aim is that it starts from the core and it becomes self-sustained, that the heat that is produced in the core, or the energy that is produced in the core, is sufficient enough to start the reaction to expand to the outer layer. So
is it that the laser doesn't keep as the laser, all you explained, when that laser starts that reaction, is it that you don't continue putting in that laser?
No. So the laser only compresses once. So it's a pulse, as it's done right now. It's just one pulse that compresses. So the aim is that force that compresses is able to start the reaction from the core, and it's self-sustained till it burns out to the outside when there is no longer any flow, right? And remember, when that happens, when you produce fusion, there's helium, there's neutron, and there is energy, there is release because of the mass imbalance.
This energy is is in form of heat, right?
There is actually about 80% of the energy is stored in the neutron.
Okay.
But remember, neutron is like a flying object, so it just flies. It's a projector. There's a way that you can capture you can stop it. When you stop a fast-moving object, right? That obviously creates heat. This heat, this is an engineering problem, obviously not a scientific problem, because physics believe that that could be converted. So you then convert this, go back to how we've always made electricity from all. In fact, the whole of human history, you can summarize it in we're finding a new way to heat a steam, to make steam to drive it drive the turbine. So it's still the same thing. Then we know we perfected the technology of steam turbine that can generate electricity. So the process we just described happening is 1 billionth of a second. So that is just one, because once the fuel burns out, that is. So for this to practically work, you'll be looking at making about 100 pulses with 100 different capsules in a second. So you'll be shooting laser at 100 times per second or even more. So, but currently, NIF, which has the most energetic and powerful laser on the planet, can only do it once a day.
Why? Why?
Yes. Obviously, the laser technology is very old. The laser technology is not. It was built in the 90s. The wall efficiency of the laser, it's about 0.5%. So it could take about 300. Okay.
What? Did you say 0.5%?
Yes, correct.
What? That's the problem.
Well, efficiency has increased. Laser technology has improved drastically since they built the facility.
Okay.
The 0.5% is now about 30 to 35%.
Yeah, because I'm like, what the hell, 0.5?
Yes, but NIF does not care about the efficiency of the laser because it's a research facility. Their aim is to study ignition. Their aim is just to understand the science of fusion. It's not to maximize the efficiency. Right, you understand? So when this is also cause confusion in the media, is that people say, "Oh, but they put 300 millijoule because the laser takes 300 millijoule from the electric grid and only produce about 3.15 millijoule from the nuclear fusion." If you look at that, that is about 1% efficiency. It's like this technology is never going to work.
Yeah.
No, for example, that doesn't make sense to most people. But you also need to keep in mind that it's just a science facility. Laser technology, for example, has been increased drastically about 70 times in terms of efficiency. We would also need to make more from the reaction, but so we can then capture the heat. Go back to the topic of capturing heat. So we'll find a way to keep firing lasers, keep making capsules, and to make these capsules, this capsule has to be the one of the most perfect things.
So the capsule is the fuel, like
is the fuel, the deuterium and the tritium.
Yeah.
Because any imperfection, it's not going to work.
So you've actually talked about a lot of challenges like research or challenges that researchers and engineers would have to overcome. You've talked about the fuel, like being able to make it in a perfect way, even sourcing it, the laser efficiency. I would like to actually read out the exact announcement from DOE so that if anybody has if they didn't know about that before, they should know, right? So that they understand where we're coming from. So I'm just going to get my phone to read it from their Instagram page. On December 13, 2022, on Department of Energy space. So they posted that there was a breaking news. U.S. Department of Energy and DOE's National Nuclear Security Administration today announced the achievement of fusion ignition at Lawrence Livermore National Laboratory, a major scientific breakthrough decades in the making that will pave way for advancement in national security and the future of clean power. On December 5th, a team at the LLNL's National Ignition Facility, NIF, conducted the first controlled fusion experiment in history to reach this milestone, also known as scientific energy break-even, meaning it produced more energy from fusion than the laser energy used to drive it. I'm not going to read the rest, but yeah, so that's what we've been talking about, like the first time they were able to. So, for example, if the laser energy was like 200 megajoules, how much energy were they able to produce?
Okay, so let's actually put a box to this and explain the efficiency. Because if we're going to build a power plant, we need to discuss the current numbers. At the point of ignition, which are the point where the laser hits the capsule itself, about 2 megajoule of energy, UV energy, was present in the laser that is transmitted to the capsule. From the nuclear reaction, we're able to produce 30.15 megajoule. So that is 1.5 times. In scientific time would be Q, which is efficiency, equals to 1.5. But when we then look at the entire facility, the amount of energy it took to produce the laser, that is 300 megajoule. You understand?
Yeah.
But that is because of the challenges we've been talking about the facilities. It's not a condemnation of the technology.
Yeah, of the technology. So in order for this technology to be possible or to be adopted, that laser technology needs to be improved for that.
Yeah.
Right.
So
the efficiency rather.
The efficiency needs to be improved. And as I discussed earlier, the efficiency over the decade is astronomically great. Like you have SLAC, which is Stanford Laser Center, where they use laser to do X-ray to do absorption experiments and all of other scientific stuff, which over the years has improved drastically. But currently, the number for most of the laser, depending on the wavelength, is between like 20 to 35% efficiency, compared to what NIF has is just 0.5 efficiency. So you could tell the difference is that the current number based on what we know about laser. So the Q, which would be the net energy gain, for that now is about 10 to 15 times actually. So that is way more. That is about 10 times more than what was shown that DOE showed. So if we have to adopt that with newer laser technology, so for each laser that we shoot, we'll probably be getting about 10 to 15 more energy out of it.
For each laser you shoot, you'll be getting 10 times.
Yes. So
like that's the goal.
Okay. So for example, let's go over the math again, right? So it took 300 millijoule to produce 3.15 millijoule of energy from the nuclear fusion. But if we were to hypothetically use newer laser technology, the 300 millijoule will then be producing about 3,000 or about 4,500 millijoule from the nuclear fusion, because our laser technology has improved drastically. So if we are to extrapolate based on the efficiency of the current laser.
No, but do you know why I'm still not getting it? Because we were talking about, I know we talked about the efficiency of the laser, but we were even just talking, like the DOE, they announced just the laser energy itself. They were not talking about the energy used to produce the laser.
Yes.
But yeah, like, so that's not meant to change, right?
It could change. So that is where most of the research is going to go in, especially on the fundamental aspect, is that think of it like, is there a way we can efficiently compress the capsule with less energy? That is one of the science or the research question would be, is that if we can, the minimum energy that it can take us to efficiently compress the capsule. So that is an hydrodynamic question that people are trying to answer. Is that if you can hit the core faster, or if you can compress it, maybe we need to change the direction, or maybe we need to increase the size of the capsule, and questions like that. The way the capsule is currently being formulated. So we could potentially increase the efficiency. And I think DOE itself believes that it could improve the efficiency by about 100 times.
Okay. So that's like what they think they can do, and that's what they're working towards. So is there like, just like they're looking towards 100 times, is there also, I know you said the newer lasers are more efficient and all. Is that a good, like, is there a goal of how efficient the laser should be, and like the efficiency of the laser energy to the nuclear fusion energy? Like, is there an hypothetical goal right now for these two steps?
I have not seen that. I have not seen that goal is there for lasers, but I believe laser technology will keep improving. Because we're not just using laser for this. Yes, we just lasers for a variety of things. So I believe laser technology will keep improving, and by the time this technology is ready, which probably we'll talk about that later, the laser technology could be approaching 50%, for example, 60%. So.
Yeah. So also now just thinking into the future, or hypothetically, for this to actually be clean energy, what should be used to power the laser?
Okay, that is a very, 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 very good technical question, or climate question. Like, if you're burning coal to do that, does it really worth it? So this also reached the question of the importance of this to climate change. Is this going to contribute to climate change? This technology is not developed yet. We know it's possible because we've done it and we can repeat it. It's a science. It's science, right? But in the meantime, we need to keep working on the current technology, the technology that we know are in work, solar technology, geothermal technology, the wind turbine technology, the diesel technology that we work on. So these, I believe, by the time this technology could be commercialized, the other technologies could add to kickstart the process.
Yeah,
I mean, once the process becomes sustainable, so you have the first energy production from your nuclear power plant, you can recycle the energy back to
exactly.
Yeah. But so the question is always about the first one, and I don't think the first one is as significant. It will be significant compared to the gain we're going to make from this technology.
So let's talk about safety. How safe? I know we've touched on the environmental impact a little bit, but how safe is this technology? Because when people hear nuclear, they get nuclear disaster, Chernobyl. So how is this safe? Yeah.
Yes, that is why everybody is excited. Actually, it's because of the safety. And if we're talking about making energy from nuclear fission gives us that, and very clean as well in terms of carbon. But the problem is it makes radioactive waste. Nuclear fission now.
That's with the eye fission. Yeah.
There is stored, so you need to store that over hundreds, if not thousands of years. And we know that we're probably causing problems for future generations because we have limited resources in terms of land. When we run out, or what if future archaeologists decide to go open one of those sites? In fusion, one of the four deuterium, it's not radioactive. We use deuterium in the lab all the time. The titanium is radioactive, but its half-life is only 12 years. So it's extremely short-lived. And remember, it's also rare. We don't need a lot of it.
Compared to uranium, is what was the half-life? So we understand the comparison.
Uranium, we're talking about, I can't give the exact number. It's about 200 years or so. So you have to store that for a very long time, right? Uranium 239.
Yeah. So T is still radioactive, but
so it's radioactive, but it's easily quenched. The condition for nuclear fusion to be sustained needs to be perfect, like we just been describing. Any imperfection is quenched. If the pressure and the temperature is a little bit off, it automatically stops. So the probability that you're going to see a power plant on fire from nuclear fission is extremely almost impossible because the condition on Earth does not support a self-sustaining nuclear fusion. We specially created it. You understand? So that is one of the engineering problems that you need that can hold the condition. We're talking a very high pressure of gigapascal. We're talking of millions of degrees Celsius. Right. So you can't just, once you have that condition, the reaction stops. The major problem I potentially see is titanium probably seeping into water.
Exactly. Yeah.
It can fall if it seeps into water. If it seeps into the air combined with oxygen, it can form an isotopic water that is radioactive. But that also can easily be combusted because you can easily dilute it. Titanium is not in extreme mass on it.
You say you can easily dilute it, but you also said So are you saying like if you dilute it, it will not be harmful?
Yes, it's naturally occurring in water and seawater, but it's just in
Okay.
extreme minute amount. It's in minute amount, right? So
Mm,
if you dilute it, if you dilute any poison,
mm.
it's
So, but I'm wondering, like, if you can easily dilute it, then why are we even talking about the half life if, like, all the waste can just be diluted?
yeah, it could be diluted, and
Yeah.
even in dilution, we know that with 12 years, it's going to degrade. It's going to decay anyway.
Okay. Okay.
So
So, but what are the potential side effects and risks of this nuclear fusion?
the potential side effect would
Mm,
be the worst case scenario that could happen would be you having a tritium leaking into the air and people
mm,
directly in any that would be catastrophic. But
mm.
the probability is extremely low.
This
So
is
the
true.
safety is it's one of the safest technology that we would be able to develop, and that is where you see we have this utopian feeling around nuclear fusion because it gives us unlimited energy. It gives us carbon-free energy, and we also believe that it's extremely safe
Mhm.
for humans.
So, do you think the technology will reach, like, will ripen fast enough to help in this clean energy transition stage? Um, what really can it really play a role now, seeing that the technology is not mature enough, and like we're really trying to reduce our emissions and all? Do you think it will actually play a role?
Now, now is a capital no. It cannot help us now.
No.
We just made the first baby step. When Wright brother developed the flight, the first one, it took about 44 years. They were able to develop a supersonic flight jet. But could it take that long? Could it take 20 years, 30 years? DOE believes 10 years. We understand DOE is a political organization, and obviously, but which is a little bit like almost impossible given the challenges that this technology is facing right now. But if there's any sort of
Because
hope,
like sorry because like when are they
yeah,
going to build a plant on the moon?
as regard that, UK, they just it got 570 million funding
Oh,
to develop tritium on Earth
oh, from where? Lithium?
from lithium.
Oh, that will really compete with our battery. Anyway, I don't know. Like
Yes,
with the battery stuff.
it's gonna
Yeah.
compete with battery technology,
Okay.
obviously. So that's why battery technology needs to pick up at some
Mm.
point. Yeah. So there is a lot of private sector involved, so which makes me believe that it could be sooner than we thought it could be. I would
Mm.
I would believe about 2 to 3 decades. I'm very optimistic, but that is the optimistic side. So you have to be if we have to be realistic, it probably take about 40 to 50 years. So
Okay.
immediate challenge is that we need to get working on climate change. You know obviously what the goal is before 2050,
Mm-hmm.
where there might be a point of no return. So
Mm-hmm.
the aim, all hands still need to be on deck for the technology that could help us fight climate change. But if any case we're able, which I believe in humanity, that we're able to solve this problem, if when we're able to solve this problem, on the other side, there is an holy grail of energy. There is a future
Mm.
for the children, for our grandchildren, for
Yeah,
our
yeah.
future children, where they would not have to worry about energy.
Yeah. That makes sense. Let's continue fighting on our climate change. Yes, this technology is important and all, but we might not help us in our 2050 goal,
No,
right?
no,
But what's the post? Like, we need a very clean, whatever, no carbon
no
post.
carbon
Yeah.
future.
So, this is potential for that future. Thank you very much, Shola, for
You're welcome.
really walking us through this technology and helping us understand it better. And yeah, so thank you to everyone watching for watching till the end. If you have any questions, leave it in the comment section on YouTube. Follow us on Instagram at Sustainability Nuggets. I'm going to be leaving Shola's details in the description in case you need to reach out to him to ask him any research related questions. So thank you guys, and I'll see you all in my next episode. Bye. Thanks so much for listening to the Sustainability Nuggets podcast. I am Rarsu Marabi.
And I am Tosin Folarunshaw. If you enjoy this podcast, please leave a rating and review on wherever you listen to your podcast.
You can also show your support by signing up for a small donation to help sustain future episodes. You can find all relevant links in the description. See you in our next episode.